So, what we're going to take a look at now is just a brief overview, so we've got a resource to look at for how we solve projectile motion problems. Okay? So without solving a specific one, I'm going to just go through and give an idea of exactly the steps that we use whenever we deal with a projectile motion problem, at least the preferred ones. Okay? So, I haven't necessarily emphasized this enough, but you've seen it in all of the times that I've solved one, so I'm going to go through the steps so that we see them specifically, okay? What you want to do is you want to draw out your problem, and so if I've got one where I'm firing off of a ledge, I'd draw like that, without the little bend there, but you guys have an idea of what that looks like. I would usually put a vector like this, marked with my initial velocity and the angle it's fired at, and then I'd mark some things like this is my delta y, or what changes in the y direction, the height of the cliff. This is my delta x, my range, usually what I'm looking for. Basically any parts of the information that I have, or information from the problem that I have, I'll add in here to make certain my drawing is complete. Then, and I can't stress this enough, draw out a little chart, a table. You'll see it in every one of them that I've done, including the one-dimensional kinematics. I use it all the time. I have the x dimension and the y dimension. Because we know how to deal with kinematics in one dimension, this is kinematics in two dimensions, so all I'm going to do is I'm going to split it into two one-dimensional kinematics problems. Okay? So I make a table of all the values. There's delta x, there's final velocity in the x, there's initial velocity in the x, my time, and my acceleration in the x. Okay? In the y, I've got the same thing. I've got delta y, my displacement in the y, my final velocity in the y, my initial velocity in the y, my time, and my acceleration in the y. And as we've talked about before, I don't have a subscript on the time because however long it's flying in the x direction, moving this way, is the same amount of time that it's falling in the y direction. The motion takes place in the same amount of time. They both begin at time equals 0 when I fire the object, and they both end at time, whatever the time happens to be, right before it hits the ground. And we always have to look right before it hits the ground, not after it hits the ground, because when it hits the ground introduces a force which changes the acceleration. In other words, while it's falling in the y direction, we just have our regular acceleration, which is gravity, which is negative 9.81 meters per second squared, assuming up is our plus y direction, and to the right is plus x. That's usually how we do things. But if I have down being my plus y direction, then that'd be a positive 9.8 meters per second squared. Okay? But while it's flying through the air, its y acceleration is just gravity. When it hits the ground, there are forces that happen there, and our acceleration is all sorts of stuff that isn't just gravity trying to speed it up. We've got stuff with the ground. It stops accelerating. It actually comes to a stop effectively there. But the thing that slows it down and makes it come to a stop is using a different acceleration. And the equations that we use, they can only be used when acceleration is constant. So we can only use our equations to predict from the point that it's launched to right before it hits the ground. Because when it hits the ground, its accelerations change, and we can't use our equations anymore. But we've got our table here, so we fill in any of the information that we have. Our acceleration in the y, it's usually gravity. Our acceleration in the x, usually 0. I don't know, maybe I'll put a rocket engine on one of our projectiles at some point, and then our acceleration might not be equal to 0. But unless you hear something to the contrary, if we're ignoring air resistance, it's 0. We'll fill in any of the other information we're given. Usually we're given our initial velocity, it's our total velocity, and some angle that it's fired at with respect to the horizontal. Well, we've got an x component of our initial velocity, and we've got a y component of our initial velocity. Those are our initial in x and initial in y. So we can solve that vector to put in these numbers. We fill in our table with any of the variables, the pieces of information that we have. We see if we've got enough, say, in one dimension, usually the y, to solve for usually time or some other value, if that's what we're looking for. If I'm looking for the impact velocity, you might be able to solve for it just by looking for that guy. But usually we'll solve for time because that's our bridge between the two dimensions. We solve whichever side we have more information on. We go over through time and we can find out stuff in the other dimension. Okay? And so in the end, it's just filling in this table. It's a quick and easy way to see exactly what you've got. As soon as you've got 3 values on one side, you can usually solve for any of the others, because our kinematic equations have 4 variables each, so if you know 3 of them, you can solve for the 4th one. Okay? And so you just go through with your kinematic equations, find the ones that you want, just like we did in one-dimensional kinematics, and then you plug in your values, get your answers. Okay? But drawing it out is a good first step. It isn't always necessary, but it can be useful, especially when you're new to it, to help visualize what's going on. Declare which directions are your positive directions so you can keep track of your pluses and minuses. Then draw your table where you can put all of your information in. If you have vectors, resolve those vectors into components because we're looking in the x direction and the y direction. Get those filled in on the table and then see what you can solve for. Hopefully you'll be able to solve for what you're looking for.